Hi, this video is about chapter 11, rotational dynamics and static equilibrium. In this chapter, we will learn a new concept. It's called torque. It's about rotational force. You can think of it as rotational force. And we will also learn about applications of torque, angular momentum, and conservation of angular momentum. So you know that it's hard to carry a bag like this or also like this, but it's easier to carry a bag like this. So you don't see anyone really carrying their bag like this or this, but everybody carries it like this on the shoulder. So why is so? It's harder to hold the bag at a larger distance. So this distance, it's important here from the axis of rotation. So the axis of rotation here is the shoulder. Why is this hard and why is this easy? Well, this is related to the concept of torque. Torque is the tangential force. So if you remember, we were defining tangential acceleration or tangential speeds. Now we can talk about tangential force. Tangential force is basically, it's the force which is perpendicular to this distance to the axis of rotation. So torque is the tangential force, and it's related to both force. It's related to the magnitude of the force. So here it's, in this case, it's the weight of the bag. So we can say mg. And it's also related to the distance from the bag to the joint. So it's also related to this distance. Let's call it r. So this is the hardest for the same mg down. Okay, and here there's mg. So this case is, in this case, it's the hardest because r is, it's the distance is maximum. Here the distance is half. This is relatively easier, but in this one, r is almost 0, so this one is the easiest one. So here the torque due to mg is 0. Here there's some torque, and here there's the torque is maximum. So the torque is not only related to the force, it's actually related to the force and the distance. So torque is tangential force. It's coming from the Latin word torquere. It means to twist, turn, or turn about. The formula for the torque is basically the distance times the force times the sine of the angle, and that angle is the angle between r and f. So for example, if you want to calculate torque, let's start with this animation. So the torque here is, it's going to be, well, r is given as L, and we're going to multiply by force. And what is the angle between this distance and the force? Well, it's 90 degrees, so it's going to be sine 90 degrees. And we know that this is 1. So in this case, the torque will be L times F for this wrench. So is it positive or negative? Now, the convention is if the rotational tangential force, which is torque, if it's rotating the object in this way, it's negative. So if it's clockwise, negative. So in this case, it's actually, we need a negative sign here. If the torque, if the force or the torque rotating the object in the counterclockwise direction, then the torque becomes positive. So this is just a convention. Okay, what about the torque here? Well, the force is mg, okay, here. The length is from the force to the axis of rotation. The length is L, and the distance between, the angle between them is 90 degrees. So in this case, the torque is L times mg. But in this case, the force is again mg, the angle is the same, 90 degrees, but the length is L divided by 2. So just because, even though the forces are the same, but because this term, which is R, in this case, it's smaller. So we have a smaller torque here. That's why this case is easier to carry a bag like this is easier than this one. Because the bag here, it applies less torque on the arm than here. Okay, so again, this is the formula and this is the convention. If it's clockwise, the torque becomes negative. If it's counterclockwise, the torque becomes positive. Here I put positive or negative, so you have to determine if it's positive or negative with respect to this convention. So if we have a wrench like this, let's say we can apply by our hand force F. Okay, you have two options. You can apply it here at the distance R1, or you can apply it here. It will be the distance R2. Okay, if you apply it here, the torque will be, first of all, it's going to be positive because it's going to rotate it in the counterclockwise, and counterclockwise is positive. So the distance will be R1 and the force is F. If I apply the force here, now the distance will be R2 and it's again the same F. So if you compare these two, this one is larger than tau 2. So tau 1 is larger than tau 2. So the torque here is larger. Even though the forces are the same, the torque here, the torque produced here by this force is larger because the distance is larger. That's actually why we hold a wrench from here. We don't really hold a wrench from here, right? We prefer to push it from the end. So we hold the wrench at its end because it creates the maximum torque due to large R. It becomes easier to tighten or loosen a bolt. So there's something called a cheater bar. It is this object here. So you have a wrench and you can combine your wrench with the cheater bar. What happens is this actually makes the length larger. So now instead of pushing here, now you can push here, so you would get more R for a given force. So what happens if you have more R, then the torque that you apply becomes larger. So you can use a cheater bar in addition to the wrench to increase the torque. Longer bars create more torque due to more distance for a given force. So it will be easier to, let's say, loosen the bolts here or here with a cheater bar than just by using just the wrench itself. Only the tangential component of F force causes torque. That's why we have a sine term in the definition of the torque. So if you imagine a merry-go-round like this, and if the kid is pushing if this kid applies a force in this direction, like pulling it, this will not create any torque. So it will not really create any rotation, right? It's like you have, let's say, you have a door like this. Okay, this is the door. If you pull the door right in this direction, it will not really create a torque, so it will not really turn the door, right? It will not open or close. It will work only if you apply a force in this direction or in this direction. If this is R, so these will create a torque, but this one will not create a torque. So here, this kit creates zero torque. But if you if this kid pulls this merry-go-round in this direction, because this force now has a a component in this direction, which is in the radial direction, this will not create any torque. So this creates no torque. But this one, it's perpendicular. This component is perpendicular. So this component will create torque. So what does it mean? If it creates torque, then it means this merry-go-round will rotate. So then what happens if you have force and radius with an angle between them, which is not 90 degrees? Well, and this is the reason of that term. You can think of this term. It actually gives us the component of the force that's perpendicular to the r. So if you look at this one, this angle is actually 90 degrees. So this one is F times sine theta. So you can think of torque as, you can use this formula, you can multiply these and then multiply the sine of the angle. Or what you can do is, alternatively, you can multiply r and the perpendicular component of the force. So both will give you the same thing. Okay, you are using a wrench, so you're going to use one of these wrenches, and these two have cheater bars added. So you're going to use, you are using a wrench to loosen a rusty nut. So these are the nuts here. Which arrangement will be the most effective in loosening the nut? So if you look at it here, so if the torque, so whichever creates more torque, that will help. That will be most effective in loosening the nut. So in this case, the torque here will be, let's call it R. It will be R times F. I'm not really writing sine 90 degrees because we know it's 1. So in this case, there is going to be some theta. So it's going to be R times F times sine theta. Now, because sine theta is some number less than 1, this case will be smaller than the first case. So that's for sure. Here, the torque will be R times F times, and even though there's a rod here long, but we have to look at the distance that's perpendicular here. So you can move this F if you want here. So as long as you don't change the direction of the force, you can move it. So in this case, again, it will be R times F, and there is 90 degrees here. Now, this one has, if you call the whole length, let's call it R, the uppercase R. So the torque here will be uppercase R times F. And because uppercase R is larger than any of these distances, this will give us the largest torque. So if you want to loosen a nut, you would use this one because this would create the largest torque. So now in chapter 10, we talked about analogies between linear quantities and angular quantities. So we will continue with those analogies. So the linear quantity is mass, and the corresponding angular quantity is angular moment of inertia. It's also called angular mass, but we will call it moment of inertia. Remember, this was about how hard to push an object. So you can think of this animation. And this was about how hard to rotate an object. So it depended on the mass of the object and the radius of the object, and also the shape of the object. So sometimes you had 1/2 mr squared or 1/3 mr squared. So it depends on the shape of the object. If you have a linear quantity acceleration, the corresponding angular quantity is angular acceleration. And now in this chapter, what we are learning is for torque, in the angular case, for force, we have torque in the angular case. Okay, so if you are pushing a box with some net force, then we know that the box will accelerate, right? So what is the corresponding equation in the angular case? Well, in this case, if you apply a torque, which means force times this radius, and let's say it's force F, so this will give you the torque R times F. So this torque will create on this object with moment of inertia I, it will create a angular acceleration. In this animation, it looks like it's rotating with constant angular speed. If that's the case, then angular acceleration is 0. But in general, if you, let's say if this is initially not rotating and then you are starting, applying torque and it will start accelerating, in that case, we will have non-zero acceleration, angular acceleration. So in this case, in the linear case, we have the larger the mass, the harder to accelerate linearly. And in the angular case, the larger the moment of inertia, so instead of mass, now we have moment of inertia, the harder to accelerate angularly. So if the moment of inertia of this object here, which depends on its mass and also the radius and also the shape, if it's a hoop, if it's a circle, or any or sphere, whatever its shape is. So depending on its moment of inertia, which is here, its acceleration, if this is large, so for a given torque, if moment of inertia is large, then the acceleration will be small. Same thing here, right? If the mass is large, this acceleration will be small for a given force. And if there's acceleration, then the speed is changing, right? So force changes linear speed, because acceleration is actually the change in speed. And if there's torque, it changes angular speed. Okay, so we talked about this figure in chapter 10 when we talked about kinematics, the acceleration and the angular speed. Now we are adding the torque to this picture. So if so let's say this is rotating counterclockwise, and if the angular speed is increasing, that means there's an acceleration in the counterclockwise direction, right? And if there's an acceleration, now if you again remember this equation, it's just like F equals ma. So if there's acceleration, then there's going to be a torque, and the direction of the acceleration and the direction of the torque are the same. So if you look at here, again, the torque and the acceleration are in the same direction. So what's happening here? It's rotating in counterclockwise direction, but the angular speed decreases. That means there is a acceleration in the opposite direction. And for acceleration in the clockwise direction, you need a force in the clockwise direction. And if you analyze all of these four figures, you will see that the torque and the angular acceleration are in the same direction. Okay, now let's start applying the idea of torque on more realistic examples. So here, find the net torque on the forearm with respect to the elbow joint. So with respect to this point, we will calculate the net torque on this forearm. Okay, so this is like if, let's say, we have a box, we have a bunch of forces, maybe, let's say, 20 newtons, let's say in the opposite direction, 8 newtons, then the question would be, let's say, find the net force. The net force would be 12 newtons. We will do the same thing, but now for the torque. Okay, so this forearm may rotate in this way or in this way, clockwise or counterclockwise, because of these forces. So some of these forces, they will try to, for example, the mg of the baseball, it's down. Now, if you look at this, if you think of this elbow joint, it will rotate this force, mg, small mg, it will try to rotate the arm in a clockwise direction, which is negative. So this will create a negative torque. Same with this mg. This mg is the mass of the forearm, the weight of the forearm, and it will also try to rotate it around this point in the clockwise direction. So this will also create negative torque. Now there's also this muscle. The muscle does not connect to the elbow joint. It actually connects somewhere here, and there is a distance, 2.75 centimeters from this point to the elbow joint. And if you look at the force, so the biceps, they pull the forearm in the up direction. In fact, that's the reason why you can actually hold your forearm like this. If this muscle was not here, your forearm would basically fall down. It will rotate down. So, and if you look at the force, it's up with respect to this point. It will try to rotate the arm in this direction, and that's counterclockwise, which is positive torque. Now, this figure looks complicated. Let's make a simpler figure. So this is the model of the forearm. We have the mg from the ball here, lowercase mg. And we have the uppercase mg, and that's the weight of the forearm. And we have the elbow joint, and we have the pulling force by the biceps. It's 12.6 newtons, and it's here. So as I mentioned, this creates positive torque, and these creates negative torques with respect to this point. Now, if you look at any other point, if you calculate the torque with respect to other points, now these may become negative and these may become positive. So it's very important to choose a point that you will calculate the torque. Now, I chose this point because I don't really know the forces here. So if I choose this point, then the forces here will not create any torque with respect to this point because R would be 0. So that's the reason why I choose this point to calculate the torque. Now, the net torque will be summation of the torques, individual torques that are created by these three forces. Okay, so let's start with the bicep force applied by the pulling force from the bicep. It's this one. So the force is 12.6, and the distance to the elbow joint, that's the point that I calculate torque for, it's 2.17 centimeters. I have to multiply it by 10 to the negative 2 to convert it to meters. Now it's in meters. And what is the angle between this radius, R, and this force? Well, it's 90 degrees. And sine 90 degrees is 1. Now for the second one, this one, so the force is the weight of the forearm, and the distance is 17 centimeters. It's written in meters here by multiplying 10 to the negative 2. And again, the angle is 90 degrees. And for the baseball, the distance is 17 plus 17. It's 34 centimeters. The mass is, it's lowercase mg, and the angle is 90 degrees. Now the angle could be a different thing. For example, so this is the joint, and for example, there could be a force in this way. Then I would take, so this is R radius, I would take this angle. But in this case, all the forces are up, down, and they are all 90 degrees with this radius, over distance. And if you calculate, if you multiply the numbers, the final result will be this. So here, the masses are not given in numerical values, so they're just left like this. But if they're given, you can just plug in the numbers and calculate the total or the net torque. So let's say you put in the numbers for the masses, and for the acceleration of gravity, 9.8. And if you find this number, this net torque, to be 0, if you find it to be 0, after substituting the values for m, uppercase M, lowercase m, and g, then that means the forearm has 0 angular acceleration. Why? Because look at this formula. If the net torque is 0, then there will not be any angular acceleration. This is just like in the linear case, right? MA. If the net force is 0, let's say we have a box, there's a force 5 Newton to the right and another force 5 Newtons to the left. F net is 0, then acceleration would be 0. Same thing here. If total torque is 0, then there will not be angular acceleration. So the forearm will just stay like this. So there will not be any angular speed. The other option is it will move with constant speed. Okay, this is the second option. But definitely, for sure, if the total torque is 0, then it will not accelerate clockwise or counterclockwise. So if this person was already moving the forearm with constant speed, and if the torque is 0, that means there will not be acceleration, so that constant speed motion will just continue. Or simply it will not move at all if initially angular speed was 0. Okay, what happens if you find a positive number here? So let's say you calculated it, you find positive, let's say 5 newtons meter. What would happen? Then that will mean positive angular acceleration. And positive means counterclockwise. So that will mean the biceps would actually, so the torque created by the biceps would be more than the torque created by these two forces. So in this case, the forearm would accelerate in the counterclockwise direction. But if you find a negative number here, then that means there's a negative acceleration, angular acceleration. And negative angular acceleration means the forearm is rotating in the clockwise direction. So there are two options. This is either 0, negative, and positive, and these are the interpretations of those three possibilities. Okay, so let's calculate the total or net torque for on this wheel for these two forces. So there are two forces given. You can see that this is going to try to rotate the wheel in a clockwise direction. So this will create negative torque. And this will try to create, let's see, this will have in the radial direction this component, and in the tangential direction this component. So this component, if you pull the wheel, so let's say this is fixed here, this will not really create any torque, right? So the torque this creates will be 0. And this component, it will create some torque in the clockwise direction, right? It will try to turn it in this way. So clockwise is positive, so this creates clockwise direction, torque in the clockwise direction. These positives and negatives are really important. If you miss them or take them wrongly, then you will get a wrong answer. So now let's sum these two torques from these two forces. The first one, let's start with this one. So the radius is 0.5 meters. The force is 15. So force is 15. I'm going to take the angle between R and the force. So that angle is given as 50 degrees. Now you may ask, so if this is the R vector, and you can extend it if you want, you may ask, are you supposed to take this angle or this angle? Well, it doesn't matter because we are using sine. Sine 50 and sine 130 degrees, it's the same number. So it doesn't matter, it's up to you. So sine 50, so this is the torque for this one. Remember, this was trying to rotate the wheel in this direction, and that's counterclockwise, which is positive torque. So that's why I have positive number, positive sign here. Now for F2, because it will create negative torque, see, this is clockwise. Clockwise is negative, so I have to put a negative sign here. And then radius is 0.5, the same thing. The force is 10, and the angle is 90 degrees, which is 1. Now do this calculation, you will find 0.75 newtons meter. So in general, there may be forces at different points. For example, you can have force at maybe here with radius 0. Let's say 4. Then in this case, you would also add here with the negative sign another force, let's say F3. So it will be, instead of 0.5, it will be 0.4 times F3 sine 90. So that will be a third torque. So in general, there may be forces in any direction at any radius, which you may, in that case, you have to add all the torques from all the forces. So far, we have calculated only this, the net torque from R, F, sine theta. So far, it's like we have only calculated the net force, but now we are doing rotational motion. So we are talking about not the net force, but the net torque. Okay, now we only calculated so far this part. Now let's start using the whole equation. Remember, this is like F equals ma, but instead here we have everything is for the rotational motion, not linear. So let's now use the formula torque net equals moment of inertia times angular acceleration to find the angular acceleration. This equation means net torque, which is here, on an object with moment of inertia creates angular acceleration. Okay, here's an example. A ceiling fan here, rotating with angular speed. So this is the angular speed. Let's call it initial angular speed. So plus means it's rotating in the counterclockwise direction. 2.75 radians per second. It is turned off. So it was rotating and then you turn it off. So you basically cut that electricity. So it will now, of course, it will continue turning a little bit, but it will slow down and stop finally because of the frictional forces. So a frictional torque of a negative 0.12 Newton meters slows it to a stop in 22.5 seconds. Find the moment of inertia I of the fan. Okay, so now this part is kinematics, right? When we deal with the acceleration, time, and the speeds, that's kinematics. And when we deal with F equals ma or torque equals I times alpha, that's dynamics. Okay, this resembles F equals ma, and this resembles V equals V0 plus AT. Okay, now why are we using this one, this equation? Because we know the final speed, angular speed, it's 0. We know the initial angular speed, 2.75. We don't know the acceleration, okay, alpha, but we know how long it took for it to stop, and this is the time. Now, if you solve for alpha, you will find negative 0.12. So that's the acceleration. So in this case, it's just, it's a coincidence. There's really no meaning behind it. It's just a coincidence. Both numbers are the same, but there's really no deep meaning behind it. Okay, so this is angular acceleration, and the units are radians per second squared. And now we are going to use this angular acceleration in the second step to find moment of inertia. So we were not able to use it directly because the torque was given. I is something that we are going to calculate, but we did not know alpha. So first we calculated it. And the meaning of negative means it's actually, so it was rotating in the positive direction, and the acceleration, or the so let's say acceleration, angular acceleration is in the negative direction. And if remember, when the angular speed and the angular acceleration, if they're in the opposite directions, then that means slowing down. So in the second step, we're going to use this dynamics equation. So the torque, the frictional torque now, this is the frictional torque. So probably there's some, let's say somewhere here, there's a friction force in this direction, and there is some radius r, so that torque friction is r times f, but that number is given to be here negative 0.12 Newton times meter. So in principle, we could calculate it, but the friction force and the radius here is not given, so we will just use the number. So this is the torque from friction. I is the variable that we're going to calculate, and this is the angular acceleration. Now you can see that easily. The moment of inertia of this this fan is 1 kilogram meter squared. Okay, so in this example, we have the arm. So the person releases his arm, allowing it to drop freely. So that means the person was holding it, his arm, and suddenly he lets his arm go down. So finding angular acceleration alpha using torque equals moment of inertia times angular acceleration. So here we will do torque divided by I. Now I, moment of inertia, so this arm, it looks like this one, a rod rotating around an axis that passes through one of its ends. So in this case, you would have to use 1/3 ml squared. So we're going to use 1/3 ml squared. And for the torque, we will use R times F. So F is mg. It's here, mg. And now for this R, we are not going to take the whole L. We're going to take, this is the axis of rotation, and this is the force, and this is the distance, which is L divided by 2. And also there's the sine 90, which is not written here because it's 1. Okay, so cancel this and this, and also cancel L with one of the L's here, and you end up with 3g divided by 2L. So this would be the angular acceleration of the arm. Now the next part is, what is the tangential acceleration? A. Remember, this is like the linear of the fingertips. So if you are, let's say, a person sitting here, small person, what would you feel, or what would you say for your acceleration, the linear acceleration in this direction? So, or tangential acceleration. We can show it by A sub t, or just A. So if you remember from the previous chapter, chapter 10, tangential acceleration of any point is r times alpha. So now r is L for this point. And alpha, we just calculate it here, you put it here. And if you do this cancellation, so you will end up with 1.5 g. Now this is interesting. The fingertips, so if you drop let's say if you drop a ball, what is the acceleration that it falls down? It will fall down with acceleration g, right? But this is strange. The fingertips are falling down with acceleration that's greater than g, 1.5 g. So that means if you have a ball here, let's say this person releases his arm, and at the same time someone is just releasing this ball, the hand, it will have more acceleration than this ball, so the hand will actually go down faster than the ball. Okay, we will explain this strange result in the following slides. Well, let's continue for now to calculate the tangential acceleration now at the middle point. What is the tangential acceleration here? What is AT? Well, we will use the same equation, except now instead of L, we will use L divided by 2. And again, these cancel each other. So the tangential acceleration here is 0.75 g. It goes down, and in fact, it becomes 0 when r is 0, because you can understand that this point accelerates. It doesn't accelerate at all, so its tangential acceleration is 0, and the tangential acceleration grows as you go further and further in the radial outward direction. Here is another example. If you rotate a hoop is this shape. It has the inside is empty. It's a cylindrical shell, and its moment of inertia is mr squared. If you rotate a hoop and a disk is it's this shape. It's the same thing with the solid cylinder, and its moment of inertia is 1/2 mr squared. See, there's a difference of 1/2. So if you rotate both with the same torque, so you're going to apply the same torque. That means if they have both the same radius. So if you apply F force here, you will apply same F, and the torque here will be F times R. Here, torque will be the same, F times R. Okay, the question is which one of the two accelerates more? Now look at this equation. This equation tells me for the same torque, if this part is fixed, same, then if you need more acceleration, then you need less moment of inertia. So here you can easily say this has less moment of inertia, so this is going to accelerate more. So you will have more angular acceleration. But let's do the calculation. So the torque, let's write the equation for this one. Torque equals moment of inertia is mr squared, and let me call the angular acceleration of this hoop alpha hoop. And for the disk, again, I'm using the same variable for torque, because it says the same torque is applied. So moment of inertia, they are of course different. This one has 1/2, and of course the accelerations will be different. So for this one, I'm going to use alpha disk. Now, if these are the same numbers, then I can equate the right-hand sides of these two equations. Here, that's what I do. So this one is this one, and this is that one. Now, cancel mr squared and put this 2 on the other side. So 2 alpha hoop equals alpha disk. So which one is larger? Of course, alpha disk is larger. You can see from here, if alpha hoop is 1, alpha disk becomes 2 times 1, it becomes 2. So the disk accelerates more. It makes sense because the disk has less moment of inertia. This is like smaller mass accelerate more under a given force. Again, you can use the analogy with the linear motion. Okay, now let's move to the static equilibrium. Now look at the figure. Look at this plank and everything, in fact, the child and the people, they are, particularly this plank, they are in equilibrium. So what does that mean? That means the plank is not going left or right. It's not going up or down. Okay, and that's not all. It's also not rotating in the counterclockwise or clockwise direction. Right? In principle, it may not move, but it may rotate. For example, if this person pulls it up at larger force, the plank will become like this, so it will rotate. But for equilibrium, when we say static equilibrium, we mean three things. First, the plank is not moving left or right. Second, it's not moving up or down. And third, it's not rotating counterclockwise or clockwise directions. Okay, so conditions for static equilibrium. For the plank not to accelerate up or down, so acceleration is 0, we need the net force on the plank should be 0. Remember, if net force is 0, then the linear acceleration will be 0. And the second condition is, so this actually, you can think of this as two conditions for fx equals 0 and fy equals 0. And this condition is for the plank not to accelerate angularly, we need zero angular acceleration. So if you need zero angular acceleration, then you need zero net torque. So the net torque should be 0. So if these two conditions are satisfied, then that means static equilibrium. Okay, let's start with the linear motion. So if there's no vertical acceleration, that means the forces are in balance. So what are the forces? So the mother pulls the kid up with force F1. The father pulls the kid or the plank. Let's talk about the plank with force F2. There's another force on the plank which is the kid's mass. Sorry, the weight. And there's also the weight of the plank itself, which is in this middle point. So if all of these forces are in equilibrium in the vertical direction, that means this plank will not move or will not accelerate up or down. So if the net force is 0, let's write the balance condition. So I will choose any force in the up direction as positive. So F1 comes with positive sign, F2 comes with positive, uppercase mg comes with negative, lowercase mg comes with negative, and I equate it to 0. And I can put mg's on the other side. And this is the condition for equilibrium, for vertical equilibrium. So if the summation of F1 and F2, these two forces, if they're equal to the summation of these two weights, then this plank will not accelerate up or down. So this is linear balance. So now let's talk about the rotational balance. So I also want this plank not to rotate if you want static equilibrium. So what is the condition for the plank not to have angular acceleration? So I don't want it to rotate clockwise or counterclockwise. Now I have to write down net torque around any point. So to be able to write net torque, remember, torque has this R inside, and R it's a distance between the force to a point that you choose. Now, which point do you have to choose to calculate torque? Well, if you look at the equation, it says any point. So you can choose any point. In this case, in this slide, I'm choosing this point. So I'm going to calculate torque with respect to this point. Now, depending on the point that you choose, you can choose the middle point, this point, this point. In fact, you can choose any point on the plank. But depending on the point that you choose, the torque that is created by these forces, it may have negative or positive sign. So in each case, if you change the point, you have to also change the sign of the torque. It may change or it may not change. So you have to check it. So let's start with this point, and in the next slide, we will choose another point. So for this point, now let's write the torque that's created by this force. This force is exactly at this point, so the radius is 0. So this force, for this point, if I choose this point, it will not create any torque. You can think of this axis of rotation as if it's fixed at this point. There's no, it's not, nobody is moving. It's kind of like fixed. It can rotate around this point. These forces can rotate the plank around this point. But if you look at this F1, it cannot really rotate it because it's already at this point and the radius is 0. Now, what about F2? So I will do F2 times L. I'm not writing sine 90 degrees because it's already 1. You can see that there's a 90 degrees between the distance and F2. Now the distance is L. It's the length of the plank. Now the question is the torque will be positive or negative? Now, if you choose this point as the axis of rotation, now look at F2. F2 is trying to rotate it. Which direction? Around it. So let's say if F2 is, if it rotates the plank, let's say the plank comes here, so it rotates in this direction. What is that direction? That's counterclockwise. Counterclockwise is positive. So that's why we have a positive sign here. So again, with respect to this axis of rotation, F2 is trying to rotate it in counterclockwise direction. So it creates a positive torque with respect to this point. Okay, that's why we have a positive sign here. Now, look at this force here. This is the weight of the plank. Now, this force is, so I'm going to write mg times the distance is L divided by 2. Now, with respect to this point, now here, this is the axis of rotation, and this is the force. If you have, let's say, a rod or something like this, if you apply a force in this direction, around this point, this force is trying to rotate it. Which direction? Now look at it. This is actually clockwise, right? And clockwise is negative. And that's why we have a negative sign here. And same with this mg, lowercase mg, the weight of the kid. So we write the force, we write the distance. So this is L divided by 2. This is the distance between this point to the kid is 3L divided by 4. And just like this mg, this lowercase mg also creates trying to rotate the plank with respect to this point in the clockwise direction, which is negative. So that's why we have a negative sign here. Because we are looking for the condition for an equilibrium, for static equilibrium, we equate it to 0. So we put a 0 here. And if you want, you can rearrange the terms. For example, you can solve for F2. Again, there's a 0, this term is already gone. So for no angular acceleration, F2 should be equal to this combination of these numbers. If F2 is something different than this value here, then that means this plank will accelerate radially. So there will be some angular, it will accelerate angularly. So there will be some angular acceleration if F2 is not equal to this number. Okay, now I'm going to move to axis of rotation here. So axis of rotation, you have to choose a point to be able to calculate the torque. But you choose it. It's arbitrary, just like you choose the coordinate system. But you have to choose one point and be consistently, calculate the torque with respect to that point. So in this slide, let's choose now this point. So in this case, now F1 will create some torque because now the radius is not 0. So I'm going to write F1 times the distance is L. What about the sign? Well, with respect to this point, F1 is trying to rotate the plank in this direction, and this direction is clockwise, right? So it will create a negative torque. That's why we have a negative sign here. F2 will not create any torque because its R is 0, so this is gone. Now, what about MGs? With respect to this point, both of them are trying to rotate it this way around that point. Now, this direction is counterclockwise, so that's a positive torque. So both will contribute positive torque. For this one, the distance is L divided by 4. For the weight of the plank, the distance is L divided by 2 because it's at the middle of the plank. Now, you can, if you want, you can solve for F1, and this is the final equation. So again, so in the previous slide, we found what F2 should be for the equilibrium. And if you are wondering what should F1 be for the equilibrium, and this is the expression for F1. So F1 should be this number, and let me go back one slide. And F2 should be this value. If that's satisfied, then this plank will not accelerate, so it will not accelerate angularly. So it will be there will be static equilibrium. It will stay just like this, parallel to the ground. Now it's your turn. Write the no rotation condition, which is just this. This is no rotation condition. Net torque around any point that you choose should be 0. So here, write the no rotation condition for these 2 points. Write it for this one first. Okay, and you will find an equation that relates F1 and F2. And in the second case, write the same condition, net torque equals 0 for this point. You will obtain 2 equations where both will involve F1 and F2. Then solve these 2 equations, simultaneously to find F1 and F2. You should get the same F1 and F2 as I did in the previous 2 slides. And the lesson here is that you can choose any point as the axis of rotation. You don't have to, it doesn't have to be these points. You can choose any point as long as you know the distances. You can choose any point as the axis of rotation. So it's just like coordinate system. You have to choose its origin and its, the directions, which direction is positive and negative. But once you choose it, you make your calculations with respect to that coordinate system. The same thing here. You choose one point and make your calculations. Okay, so in this exercise, it says write down no rotation condition for the axis of rotation chosen to be where the kid sits. So for this one, so if you do the calculation, you will find, so it's going to be your turn to calculate it. You can pause here if you want. And it will be one of these, A, B, C. And let's see if you can calculate it correctly. So you can pause here if you want. Okay, now I'm going to show you the answer. The answer is B. If you have not found it, then you just go back the last couple slides, go over them, understand really, really well, because we are going to use these concepts in the following slides. There are more examples in the book. So, for example, you can study example 11.8, which is this one, and example 11.9 from the textbook, the 5th edition. So what you have to do is you have to apply two conditions. This is for translation. Remember, static equilibrium meant no translation, not going anywhere up or down, left or right, and also no rotation. So you can use this torque net equals 0 to some of the points on the plank. So sometimes if you have more than one force that you don't know, for example, let's say you know mg, but you don't know F2, you don't know F1, or maybe even you don't know distance, some of these distances, then in that case you have to apply the second equation to different points. For example, you can, in the first case, you can apply here, find an equation between F2, D1, D2, and mg. In the second case, apply it here, you will find an equation between F1, D1, D2, mg. If we apply it here, F2 will go away, right? Because it will be 0 times F2. So that term will go away because it will not create any torque. So by applying the second equation to different points, you can get more than one equation, and you can simultaneously solve those equations to find the variables if the problem asks the distances or m or one of the f's. You can solve it. So you have the freedom to choose any point as the axis of rotation, and you can choose more than one, as we did in the previous slides. And you do the calculations according to that point in each case. If there are more than one unknown, like if both F1 and F2 are unknown, as I said, you may need to apply the condition net torque equals 0 more than once at different points. For example, in this case, there is this plank. Here, this plank is fixed on these points, but here it's different. It's just put on these wood. So if the cat moves all the way to here to the end, maybe this part will go rotate. So this one can freely rotate. So the question might be, what is the maximum distance d2 that the cat can go or approach to the end, so that the net force here will be 0. So if the cat is like this, so what are the forces on the plank? Well, there's going to be a mass. There's going to be a mass of the cat that's pushing the plank down. Remember, we are talking about the forces on the plank, okay? Not on the cat, not on these supports. We're talking about the forces on the plank. This is the plank. What are the other forces? This support pushes the plank up. So there's this force. This support normally pushes the plank up, but because the cat is here, there may be a situation when the cat all the way close to the tip or the end of the plank, the force may go to 0. And if the cat even goes further, maybe this will start rotating. Now the question here might be, what is the maximum distance that the cat, what is the maximum d2 so that the force becomes 0? To write that point, maybe if the cat moves a little bit more, then it will start rotating. But we can, ask, where does that happen, right? What is that d2 where the force, the normal force from the support on the plank starts to become 0. Anyway, this is example 11-9. You can check it out from the book. So this problem, I like this problem. It looks complicated, but it's easy. It's a equilibrium question, again, static equilibrium. So you have this lamp. It's a fancy lamp. It's connected to the wall with this piece, And there's also bolt here. So there's this bolt. Now let's relate the tension. So there's this tension on this piece. There's the weight of the lamp. We can imagine this part is weightless. So let's say all the weight is here, and we show weight here, and the force exerted by the bolt F. So this bolt, it's holding this part of the lamp here, right? It's pushing, it applies some force in this direction, in general direction. And its components, this component, it balances mg, and this component, it balances tension here. So if you, let's try to write down the equations. So first of all, the first condition for static equilibrium is no vertical or horizontal motion. So if you look at the picture, this lamp is really not accelerating up or down or left or right. So let's write down f equals 0 for each coordinate. So if it's not moving left or right, then that means fx. So I'm going to have this. So I'm going to use this coordinate system. Anything to the right is positive. So fx comes with positive sign, and tension is in the negative direction, so it comes with negative sign. So I have to equate it to 0. So from here, in fact, I find fx equals tension. Again, F force is the force that the bolt here applies on the lamp. Now let's consider the vertical motion. There's no acceleration in the vertical direction, so then Fy comes with positive sign because up is positive, defined by this coordinate system. And so Fy, what are the forces that are in the down direction? There's only mg. It comes with negative sign, so Fy equals mg. And from here, we also find Fy equals mg. Okay, are we done? No. Maybe this lamp is not going up or down or left or right, but it may rotate in principle. But we also don't want that rotation because we want static equilibrium. If you don't want rotation, then you have to write the torque equation with respect to any point. Now you can write torque equation with respect to any point, like you can choose this point, this point, this point, it doesn't matter. But I'm going to choose this point A. The reason is, if I choose this point, then I don't have to write the torque for these components of F. So it actually makes it easier, makes the equations easier. Now, if I do that, I will just write the torques for tension force and for the weight. Okay, let's start with the tension force. Now, the tension force, I'm going to write it here, and I'm going to write the distance between the tension force and this point. I chose this point to write the torque. This is like the yellow point that we used when we talk about the Planck and the kid and the father and the mother picture. So here it's the yellow point is here. Okay, so tension. Now, what is the distance between this force? Again, you can without changing the direction, you can extend the force if you want to find the perpendicular distance. Now, the perpendicular distance is this. So it's going to be V. V is the distance here. So V times T. Now, is the torque positive or negative? Now, look at this point. And the torque, the tension force is in this direction. Now, this tension force, so there's this metal here. This force will try to rotate this object around this point in this direction, which is counterclockwise, which is positive. So we need to use a positive sign here. Okay, now let's write the torque for mg. So the force is mg. Now, what is the distance between this force to this point? We are looking at the perpendicular distance. So it's going to be h times mg. And because the distance that we use is 90 degrees. So I don't have to write sine 90 degrees. And if you look at this force around this point is trying to rotate it in this direction. And this direction is clockwise direction, so that's why we have a negative sign here. So we have one equation here. We have one equation here. So here for both forces, we took the perpendicular distance. The other option could be you could take this r here. So for example, so this is like h divided by 3. This is v. Maybe you could calculate this angle, and you could do t times r. You could calculate r from hypotenuse of v squared h plus h divided by 3 squared square root. So you can calculate r from there, and calculate the angle from these variables. And you could write t times. You can write the torque as t times r times sine theta, but it will be really complicated to use this one. So that's why I wanted to use sine 90 degrees. And if you use 90 degrees, then you would basically just look at the perpendicular distance. Find the distance between points, between the point, axis of rotation, and the force. You can extend the force like this. Find the closest distance from the point to the extension of the force. So in this case, it's this distance, which is v. And for the mg, if you want, extend mg and find the distance from the point to this extension line, the shortest or the perpendicular distance. Perpendicular means 90 degrees, and this distance is h. So just because I did not know, for example, I did not know this r and the angle between r and mg, so I have not used it. I have not used r times f times sine theta because I don't really know the angle. So instead I use the perpendicular distance times force. So I use this one. Okay, so when I write the torque equation with respect to point A, I find an equation like this. Okay, this could be enough. For example, maybe M is given, G is given, H is given, maybe tension is given, maybe the question is what is V, then you can solve for V. Okay, but what happens, let's say, if you don't know V and M, so you don't know, so let's say two unknowns, then you cannot really solve this equation, right? It's just one equation, two unknowns. You can't solve it. Now, what do you do in that situation? You have to write another equation. So now we're going to choose another point. In this case, I'm going to choose this point. So I'm going to write now the torque around this point. Again, you can choose any point, but I like to choose the points that are exactly on the points where the force is, because it makes the equations easy, because now you're going to see that t times r is 0. There's not going to be contribution from t. Okay, so let's write it down. So let's write the easy part. So mg, the torque will be mg times the distance from the mg to this point and the perpendicular distance. So extend the force, find the perpendicular distance. It's this distance, which is 2h divided by 3. So mg, 2h divided by 3. Why is it negative? Let's look at the torque that it creates. Around this point, this force is trying to rotate around this point, rotated in clockwise direction. So clockwise is negative. That's why we have a negative sign here. If it doesn't make sense, pause here, try to think about it. You have a force here, and this is the point that axis of rotation, so you're calculating torque with respect to this point, and try to understand why this force creates negative force, because it negative torque, because around this point it tries to rotate it in the clockwise direction, and the clockwise is defined to be negative. Okay, now let's write the terms, the contribution for from this force here. That's the force that the bolt applies on the lamp. Now this one, what you can do is, so this is the axis of rotation, or the point that we calculate for torque. So in general, what you can do is, this is the force, and this is the distance r. So you can do r times F times sine theta, and that theta would be here. But do we know that theta in this problem? No, we don't. So then what I have to do is I have to use the components and the perpendicular distances. So instead of this force, I'm going to use its component. So don't think about the force now, just think about its components. So for fx, so I'm going to write fx. I am going to write now the distance between x component of the force to this point. Now the distance is, if you extend this force, the distance is here, and this is, as shown here, is v. So v times fx. Now, is the torque going to be positive or negative? So around this point, this force would try to rotate it in counterclockwise direction. So that's why we have a positive sign here. So this object is really not rotating, but we are trying to find if, so the torque, the contribution to the torque from each force, then you can think of it, you have to think which direction does that force is trying to rotate the object around the point that you're using to calculate the torque. Now, what about Fy? So if you extend Fy, now from this point to this extension line, the distance is here. What is that distance? H divided by 3. So Fy times H divided by 3. Now I have to calculate I have to find if that contribution to torque is positive or negative. Now around this point, let's put it here. Now there's this object here that's curved like this, and there's this force in this direction, Fy. Now, so there's this object here. Okay, so if the object is fixed at this point, if you apply a force in this direction, you will try to rotate it in this direction, right? And that direction is clockwise, which is negative. That's why, again, this contribution is also negative. So you can create more than one equation like this. You can calculate torque with respect to this point, which we did. We got two independent, unique equations. If you have more unknowns, if these two equations are not enough, then you can calculate also torque with respect to this point. In that case, you will use F's, tension T, but mg will not go into the equations because now we are calculating, if you calculate torque with respect to this point. So basically the point here is you have to write down sufficient number of equations so that you can solve the variables that are asked in the question. So sometimes just one equation is enough. Sometimes maybe just writing the torque with respect to any point is enough, but sometimes you need two equations or even three equations. Now, this is one of the classic questions, examples. So this is also the example 11-11 from the book. So there is this lady on the ladder and the forces are shown. So all the forces shown below act on the ladder. So whatever force is shown here, they are the forces on the ladder. So for example, these forces are on the ladder, not on the ground, not on the wall. They are on the ladder. They are not the forces the ladder acts on the wall. So that's important. So our point of interest here is the ladder, not the person, not the wall, not the ground. So now, what are those forces? First of all, there is a force on the ladder because of this woman. She has some weight, and that weight is pushing the ladder down. So there's a downward direction here. Because this end of the ladder is on the ground. The ground, there's a normal force from the ground. So this is a normal force. We can show it by N or F1, doesn't matter. That's a normal force. Now the ladder wants to, so it would naturally slide to the left, right? If in this case. Now if it's not sliding to the left, there should be some force that's keeping it, and that will be the friction force. So F2 is actually the friction force on the ground. Also, if this ladder, if it slides to the left, this part, then this part, the top part would slide down. And there is this force F4 that keeps it not slide down, and that's also a friction force on the wall. And because the ladder is touching the wall, there should be some normal force from the wall. That's also a normal force. So this is also a normal force. So if the wall is frictionless, that's possible. Let's say there's a friction on the ground, but the wall is frictionless, then there's no F4. So F4 could be 0. In that case, even in that case, the ladder can still stay without sliding down since there's a frictional force F2 on the ground. So even if there's no F4, F2 would be enough to keep it here. Now, why does it sliding down? Why is it going this way? Or what is the force that makes it? Well, it's actually this force, the normal force from the wall. We'll try to push the ladder this way so that the ladder slides, this part slides, but this F2, if it's large enough, can keep the ladder as this, not sliding. Okay, so even if there's no F4, F2 can be enough to keep that friction, can be enough to keep the ladder like this. But without F2, if there's no F2, even if there's F4, without F2, the ladder cannot stay up. It would slide down because there wouldn't be any force to balance F3. Remember, for static equilibrium, you need no rotation. You also need the forces on the horizontal and the vertical should be equal. Now, look at the force here, this normal force. It's to the left. It's on the horizontal. Now, is there any force here that can balance it? That's only F2, right? There's no other horizontal force that could balance F3. So the only way for this ladder to stay like this without sliding is by means of this friction force F2. If there's no F2, even if you have F4, this will slide and the ladder end will move to the left. Okay, so vertical and horizontal forces and the torque on a forearm hung by a sling. So now we did a similar problem here. The difference is we have now another force, which is in this direction. So it applies a tension force in that direction with some angle. So there is going to be also, in general, there's also a force from the bicep here. That force is pulling up, but because probably this is a broken arm, we assume here the bicep is not really pulling, or maybe that person could not pull his arm because of some injury. So in that case, the bicep force will be 0. So what would the force that balances the weight of the forearm would be the tension force from the sling. So all the forces shown here act on the forearm, not the upper arm. So forearm is this one. So now you may wonder, which direction should you take the force from the joint on the forearm? Is it going to be that way, this way, this way? So you may not know it initially, but don't worry. Don't worry if you are not sure about how to choose the direction of fx and fy. So here fx is to the right, fy is in the up direction. But in general, could be, fx could be in this direction, fy could be up, then the force could be in this direction. But you don't have to guess it right, okay? So just make a guess. So just make a guess. You could start from this picture here, or just like this for fx and fy, and do your calculations. And if you find them to be negative, let's say at the end you find fx equals 5 and fy, let's say fx equals -5. So let's say you chose this one. You find fx equals -5, fy equals 7. So if you find them to be negative at the end of the algebra, that means you initially showed them in the wrong direction. So now this means we got fy as the correct direction. But if you find negative for fx, let's say, that means we chose fx direction initially in the opposite, in the wrong direction. So that means this tells us the correct direction should be fx should be in this way, and fy is in this way. Again, this doesn't have to be the correct answer. It depends on the problem. Fx and fy, they can be in any direction. But your calculation, so you don't have to know which direction to choose. Just choose any direction, make your calculations. If you find any of them or both of them negative, then that means they are the correct direction is actually the opposite direction. Now remember, tangential acceleration, A, of the fingertips was 1.5 g. We calculated it when this person releases his arm. The tangential acceleration at the tip was actually more than g. It was 1.5 g. Now, how is it possible that something can fall with acceleration more than g? Now, here we are going to explain it with this figure. So this here, you can think of this rod as the arm. It's the same idea. So there are a couple of dice on it. And as the rod falls down, as it rotates down, you can see that this tip, so all of these dice, they fall with acceleration g. And you can see the tip of the rod is actually, because it has more acceleration, it falls down more than the dice. So how is it possible? How can something fall down with acceleration more than g? Now here's the explanation. Ignoring a resistance, the dice are affected only by gravity, and they fall with acceleration g. Now the end of the rod falls with, so this end falls with tangential acceleration given by r times alpha, and that's greater than gravity, since, now here's the explanation, why? Since the force at the pivot point rotates the rod, this is the pivot point, and because it's fixed on the wall, that there is going to be a force due to this bolt on the rod. So let's call it that force F. So the force F here, this one, at the pivot point rotates the rod clockwise. Now you may say, well, this is not really rotating it, it's fixed here. Yes, but if physically, yes, it doesn't rotate, but mathematically, if you think of the rod, this rod, there is this mg of the rod, and maybe there is also mg from these dice, but we can ignore them, they're light. So, but there's also this force. This force creates some torque with respect to any point. You can think of any point. So you can think of the rod as there is this mg and there is this F. So these would create a torque both in the clockwise direction, right? Both create torque in the clockwise direction. So you would expect this rod to rotate like this. In fact, that's what's happening here. But that rotation, so if it was just mg, it will just fall down straight, like it would just fall down like this with the dices at the same rate. But if you now think about the contribution of this force, that's an extra force on the rod. It's not just mg, just like these dice. There's mg on the rod because it has mass, but there's also this force that makes it rotate. So that's why this tip goes down faster than g. So the force at the pivot point rotates the rod clockwise, and it creates extra acceleration for the rod in addition to g. And that's the explanation why the fingertips here, they are falling faster than g, or here again, why is this, the tip of the rod is down, it went down more than the dice, more than the die here, the white one, that was falling with acceleration g. So with acceleration g, if this white one can come from here to here, and you can see that the tip of the rod came down more because it has more acceleration. Okay, let's talk about now center of mass and balance. If you hang this brush from this point, and because this is it has this shape and its center of mass will be somewhere in the middle. Now the line from the hanging point and the center of mass, if they're aligned like this, then there will not be any torque, right? This mg will not create any torque because mg, the force is already passing through this line. Or if you think of the perpendicular distance between mg and this point is 0 because it's already at that point. But if you look at this figure, if the brush is like this, there is mg here, and from the force to the axis of rotation or the hanging point, there is some distance and there's some angle. So you can write the torque here as d times mg. So you can use, if you want the perpendicular distance to the extension of the force, it's d times mg. That's one option. The second option is you can write mg times perpendicular distance, which is this distance. So mg is the force, and this is the point, the perpendicular distance. If this is theta, then if this is r, this would be r times sine theta, and that's the second case. Now the third option is you can use now the components of this mg. So one component will be like this, the other one. So these are the components. Now with this, if this is theta, then this is going to be theta as well. So if this is mg, then this will be mg cosine theta, but this will not create any torque, right? It already goes through the axis of rotation. This component will create torque. So if this is theta, then this will be mg sine theta. So what I can do here is now r times, now there's r times mg sine theta, and that's what's here, r times mg sine theta. So I'm not really using any other sine. Well, you can write it if you want, sine 90 degrees, but it will be just one. So the point here is, by the way, if you look at here, d is equal to r sine theta. You can see it from here. So sine theta equals d divided by r. So r becomes d sine theta. So d equals r sine theta. In fact, here on the third line, we have the same thing, r times sine theta. The point here is you can use, you can write torque in different ways. So it's up to you to use whichever you like. But the point here is also that there's some non-zero torque here. So, and what is the sign of it? Well, if this is the axis of rotation, if this is the force that creates torque, it tries to rotate the brush in this direction, right? And that direction is clockwise, so that's why we have a negative sign here. And torque, it depends on the angle at any point, this angle, as the brush comes, let's say, it becomes like this, maybe like this, and that angle will be smaller. So it will be smaller and smaller, and until when the brush becomes completely vertical, the angle goes to zero. So as the position changes, the torque also changes because it depends on the angle. So the torque will decrease as the angle becomes smaller and smaller, and torque becomes zero when the brush becomes vertical. So that's this case. When an object is hung, its center of mass and hanging point will lie on the same vertical axis. So this is like half circle. So if you have a full circle, the center of mass is at the center. But if you, let's say, you remove this part, what happens to the center of mass? It will move to this point. So this is the center of mass. So for this object, the center of mass is somewhere here. Now, if you hang this object from this point, what will happen is this object will move until the hanging point and the center of mass, they are on the same vertical axis. So here's the vertical axis, is what's meant is this dashed line. To find the center of mass of an object, let's say you have a complicated shape like this, and you want to find the center of mass of this object. So what you do is you hang it from different points. Usually 2 points are enough, and trace a vertical line each time. So let's say you hang it from point A and draw this line on the object. And in the second case, you hang it from B here. You hang it from B. So this is the first vertical line that we drew in the first case. Now, when you hang it from a different point, it can be any point. So let's choose this point, and you draw another line, and you look at where the line meets, and the center of mass will be that meeting point of the lines. Okay, we continue with balance problems here. So let's say we have a couple of food, or it can be any object. They are hung as shown here. It looks like a complicated setup. Let's say they're all in equilibrium. There's a static equilibrium. They don't rotate. There's no torque. And also all of these tensions they carry, or the strings they carry the objects. So here there are 3 unknowns. Find M1, M2, and M3 is M1, M2 is the broccoli, and M3 is the slice of the bread. So how do you find it? Well, simply apply net torque is 0 and net force is 0 at various points. So let's start with this point, right? This point. So we're going to apply net torque equals 0, and we're going to choose this point as our axis of rotation. So we will calculate the torque with respect to that point. Now there are two. So what are the forces? Well, there's a force in the up direction, but that force will not enter into torque equation because the radius of that force is 0, because we chose that point to calculate the torque. What are the other forces? Well, there's this force. It's a pulling force down. And there's also this pulling force because of the meat. But notice that we are looking, all the forces are shown here, are the forces on the rod. We are interested in the rod. Let's write down the torque for each force. So there are two forces then that we're going to use to write the torque. The first one is T2, tension 2. Now, first of all, what is tension 2? Well, it will be M1 plus M2G, right? Because these are pulling it down, M1 plus M2G, or M1G, M2G. You write it like this, M1G and M2G. So these will be the forces here, right, on the tensions. And also M1G. If these two forces are pulling it down, what should be the tension force here? It will be M1G times plus M2G, right? Because the tension force here should balance these two forces. So the tension force here is balancing these two forces, and that's, at every point on this string, the tension force is the same. Here, this M1 times G plus M2 times G, it's a pulling force for this rod, but for this rod, it's pulling it up. But for this rod, it's the same value, but it's pulling down. This force is pulling down this rod. So we are going to write 6 centimeters times M1 plus M2G. Now, with respect to this point, the torque is in this direction. This force creates the torque. In this direction is counterclockwise, so it will be a positive torque. That's why we have a positive number here. Now, I'm not going to convert it to meters, the 6 centimeters, because, if I use centimeters consistently, they will cancel out each other. So it's up to you. You can convert it, or you can just leave it. You can just use centimeters here. So for this one, for this force, so it's basically mg, mg will be 0.3 times g. So 0.3 times g. And we're going to multiply by the distance, which is 24. Now, why is it negative? Because it tries to turn this rod around this point in this direction. This direction is clockwise, which is negative torque. So that's why we have a negative sign here. Now, I know G is 9.8, and so I can solve for, I cannot find M1 and M2 separately here, but I can solve for this equation for M1 plus M2, and that's what we have here. So the summation of them is 1.2. Okay, now use torque net equals 0 now for this point. So it's going to be 12 times M1G. Remember, this force is M1G. This force is M2G. So 12 times M1G, and this creates positive torque, and this creates negative torque. So this one comes with negative sign, 18 times M2G. Okay, so from this equation, I find this equation. Now, look at this one and this one. I have two unknowns. I have two separate equations that are independent. So I can solve for M1 and M2. In fact, this is the solution. Okay, now finally, how do you find M3? Now to find M3, apply torque, net torque equals 0 to the upper bar. So apply it here. And if you do that, you will find M3 to be 0.987 kilogram. So I'll leave it to you to calculate M3 by applying torque net equals 0 to this point. Okay, now we come to the section where it's about dynamic applications of torque. So in this exercise, we have some rope is wrapped around the pulley, and the rope gets unwrapped as the mass falls down. So this rope is glued here to the pulley. So as the pulley rotates clockwise, the rope unfolds, so the rope goes down. Okay, only this part is glued, only this part is fixed. So the rope goes down and the pulley rotates. So there's no slip. The point why I tell you this, that it's glued here, it's to emphasize that the rope doesn't slip. It only goes down, the rope goes down as this pulley rotates. Okay, the question is now find tension, linear acceleration of this mass, and also angular acceleration of this pulley. Okay, first of all, let's show the forces. So on this object, the block, the forces, there is a mg down and there's a tension force. And what is the force that makes this pulley rotate? Well, there's this, it's again the tension force. It will create some torque and it will rotate the pulley. Now, the first thing that we have to do is we have to show the coordinate system, because it tells us which forces or torques that we have to take as positive or negative. So here's the coordinate system. Now, the linear part of the coordinate system and the rotational part, they should be consistent. So if we choose, if our convention is counterclockwise is positive, then in this case, here, this part up direction should be positive. So as you can see that it's consistent. So this one and this one, they're consistent. Okay, so we chose our coordinate system. Now we can write the torque equation for the pulley. We don't really write F equals ma for the pulley because it's not going anywhere, up or down or left or right. The only motion that it can do is rotation. So for rotation, we write net torque equals moment of inertia times acceleration, angular acceleration. Now, what is the torque? Well, I'm going to write the torque for all the forces that acts on the pulley. Well, there's only one force, right? It's just the tension force. Now, the radius is r, and the angle is 90 degrees. So it's RT sine 90 degrees. Now, because this tension force, it's trying to rotate the pulley in the clockwise direction, we need a negative sign here. Now, what is the moment of inertia of a disk? Well, you look up the table and you will find it's 1/2 mr squared. M is, notice, we have two m's here, lowercase and uppercase. Here I have to use the uppercase m because that's the mass of the pulley. And r is the radius of the disk, the pulley. Now alpha, you can, if you look at here, you can write alpha as a, the linear acceleration divided by r. R is, you know, it could be any point. If I ask you what is the linear acceleration at these points, then you would use different r. But now we are interested in the linear acceleration at this point, because we will relate the linear acceleration of the pulley at the rim to this object. How? Because whatever the linear acceleration of the pulley here at the rim, it will be equal to the linear acceleration of the rope. So that's why I'm using uppercase R, which is all the way at this point. Again, if you have a pulley like this, it's rotating clockwise. So we can talk about linear acceleration at different points. They have different value. And at the rim, it's maximum. I'm interested in finding this one. Why? Because if I find the linear acceleration at the rim, I can say, well, because the rope is also at the rim right there, I can say whatever linear acceleration the pulley has at the rim, it will be exactly the same linear acceleration of the rope. So that's why I use uppercase R here. So we can make a couple cancellations. So this R cancels one of the R's here. This R cancels the other R. And now if you so sine 90 is 1, so you end up with negative tension T equals 1/2 ma. Now in the second part, we will write F equals ma for the mass. Now, so this is now our coordinate system. The tension is in the positive direction, so it comes with positive sign. Mg is in the negative direction, it comes with negative sign. And because I'm writing the dynamic equation, F equals ma, for this mass, I have to use the lowercase m times this will be the linear acceleration of this object. Now, notice that I'm using the same acceleration because this acceleration, it's the acceleration that corresponds, because I use r here, the radius of the disk. This acceleration now corresponds to acceleration at the rim. And because the rope is also exactly at the rim, so whatever that A is, it will be the same acceleration of this rope. And also because this block is connected to the rope, it will be the acceleration of this block. So the tangential acceleration A on the pulley's rim and the linear acceleration A of the mass m are the same. Okay, what do we do in the next step? We basically solve simultaneously which equations? That's equation 1 and equation 2. So there are two unknowns, which is A and tension. We have two equations, then we can solve them simultaneously. And the answer for the acceleration is this term here. And for the tension, it's this thing. Now, here we find acceleration to be negative. What it means is, now look at our coordinate system. Up direction is positive. So if the acceleration is negative, then that means this block is accelerating in the down direction. And if you look at the figure, that makes sense. If you have a system like this, the pulley will, this mass will pull the rope, and the rope will make the pulley rotate in the clockwise. So this mass will go down. That makes sense. For this coordinate system, the acceleration is 0. Okay, this is a similar question. Now, in this case, instead of a rope that's fixed at this point, now we have two objects. And again, we choose our coordinate system. If this is, this is our convention, counterclockwise is positive. So that means the linear part here, it should be also consistent with this one. So basically, we define anything that rotates or goes in this direction as positive. You can see it here, down is positive, here is up is positive, and again, if it goes in this direction, it's positive. Okay, now what do you do? What you do is, again, you write the torque equation for the pulley, and you write F equals ma for each mass. The question here is finding the linear acceleration of the masses. So the torque equation for the pulley, now instead of one equation, in the previous case, we had only T1, we had negative T1R, but here we have also T2. And the torque, because of the T2, is positive. Now look at here, this is the axis of rotation, this is the distance. This T2 is trying to rotate the pulley in this way, and T1 is trying to rotate it in the clockwise. That's why this is creating positive torque, this is creating negative torque, and you can see that T2 has a positive sign, T1 has a negative sign. And for the disk, again, we are going to use 1/2 mr squared. And for alpha, if you want to go to linear acceleration, again, for different points, for different radius or distance, there are different acceleration, linear acceleration. But since we want to relate the motion of the acceleration of the pulley to the string, to the rope, we have to consider the linear acceleration at the rim. So at this point, so right outside point, because whatever the pulley has linear acceleration at the rim, it will be exactly equal to the acceleration, linear acceleration of the rope. So this is our first equation. So what is different? What is the difference between this one and the one that we wrote in the previous slide? The only difference is this term. So in the previous one, it was just negative r times t1, but now we have, because extra force here, we have also this term. Now it's possible that you may be wondering why we have two different forces here, because in the previous lectures we saw if you have let's say Atwood machines like this, we said whatever tension here, it will be the same tension in the same rope. But that's not the case here, because this was only valid if the pulley was massless pulley. But in this case, we have a massive pulley. So if you pull it with T1 here, that force, that force will go into the rotational energy or rotation torque of this pulley. So that T1 will not be exactly equal to T2. The same tension all over the rope. It only happens in massless pulleys, but here this is massive. It has a mass. So that's why we have T2 and T1, which are different than each other. If they were equal, then we would get 0 here. Okay, now the rest is easy. We are going to write F equals ma. For this part, T1 comes with positive sign, see, because for this part we're using this coordinate system. And M1G comes with negative sign, and it's going to equal to B. So you have to be really, really careful here, because we are writing F equals ma for this term. On the right-hand side, we have to use M1. Now, when you come to this one, on the right-hand side, we're going to use M2. And what are the signs of the forces? Well, now, on this side, on the left side, this is our coordinate. So down is positive, so M2G is positive, but tension is negative. Okay, so we have 3 equations, 1, 2, 3. So we have 3 equations. T1, so there are 3 equations and 3 unknowns, T1, T2, A. Even though in this problem it's asking for what A is, you may need to, sometimes maybe you first find T1 and T2 and then calculate A. It depends on the strategy, which strategy you use to solve these 3 equations. So what I would do is I would solve for T2 here. I would solve for T1. So I would do T1 equals M1A plus M1G. And from here, I would put T2 on the other side, put M2A to the left-hand side. So it will be M2G minus M2 m2g minus m2a equals T2. So I would take this term and put it here, okay? And I would take this term for T1 and plug it here. So now this equation will be purely in terms of acceleration A. And then I would solve that equation. And this is the answer. So try to solve that equation. In fact, try to solve this problem. Try to write down the equations from scratch and try to solve them and try to see if you can find this result. So here is another variation of the same problem. Now the difference is on this side we have force F. Again, just write the net torque. So here it's going to be R times negative T because this is clockwise, this is counterclockwise, F times R. Again, this term is the same. Now for the mass, you're going to write F equals ma. So for consistency, this is our coordinate system. Anything in this direction is positive for both linear and rotational. So tension will come with positive sign, M1G will come with negative sign. Now you have two equations. And now you can solve for acceleration A, and it becomes this term. Okay, let's move to angular momentum. So remember, whatever we did in the linear case, now we are doing everything, like their corresponding angular quantities. So we did momentum, and then here in the linear case, and then we are doing angular momentum. And after we learned about momentums, we did collisions. And in the following slides, after we learn what angular momentum, what its definition is, we will do also angular collisions. Okay, so the definition of angular momentum is moment of inertia times angular speed. So let's say if you have a disk, if it's rotating this way with some angular speed, and we learned that the moment of inertia is 1/2 mr squared. So what is the angular momentum of this disk? So it's going to be 1/2 mr squared. This is the r term. Now I have to multiply it by omega. So this will be the angular momentum of the disk that's rotating with angular speed omega. And also notice the analogy between the angular case and the linear case. Instead of mass, I have angular mass or moment of inertia. Instead of linear velocity, I have angular velocity or angular speed. Okay, so we have two options that we will see in the following slides. It's either an object that rotates around itself, like a disk here, or an object that rotates around, that goes around a point. So for such cases, we will assume that this is a point particle. We can assume that all the mass is concentrated at this point. So for point particle, angular momentum is r times p. So r is this distance and p is m times v. So again, let's start with this definition. L is I times omega. And for a point particle that goes around, its moment of inertia is mr squared. If you remember, we had an object like this. It was three masses connected with some rods like this, and it would rotate around this axis or this way. And for these masses, point-like masses, we used I equals mr squared. So that's what we are using here. for point particle that goes around a point, not around itself like the disk, but goes around a point, its moment of inertia is mr squared. And the definition of omega is also linear speed divided by r, or here. So instead of omega, I'm going to write v divided by r. So this 2 and r, they cancel each other. So what we find, r mv. And if you want, you can write mv as p. So the bottom line here is the angular momentum of a point particle like this that goes around a point of radius r or distance r, then you can write its angular momentum like this. For the disk, I cannot see the angular momentum of a disk is like this, because the disk is rotating around itself, not rotating around, in this case, around anything. But here, this object is rotating, it's going around some point. So in this case, you can use this one for point particles that goes around a point. So to summarize, if an object like a ball, child, etc., goes around a point, like here, but not rotates around itself, like here, then you can assume it's a point particle, and you can use L equals R times P or R times mv for its angular momentum. Here, uppercase L is angular momentum. Okay, so angular momentum of a linearly moving particle. So even though a particle can, even if it's moving linearly, we can still talk about its angular momentum with respect to some point. So angular momentum of a linearly moving particle, let's say this particle is moving on this line linearly, with respect to a point, is momentum times perpendicular distance. So that will give us the angular momentum. So let's say, what is the angular momentum of this object that moves in this way with respect to point A? Now what we're going to do is we're going to do R times P, and P is m times V. Now R perpendicular, this sign means perpendicular or 90 degrees. We have to find the distance between the point to the particle's trajectory, linear trajectory, and that distance is d. It's going to be d times mv of the particle, so m times v. Now, is it positive or negative? Well, now look at, with respect to this point, as the particle moves in this direction, so as the particle moves in this direction, around this point, this is like the counterclockwise direction, right? This looks like the counterclockwise direction. So counterclockwise is positive, so then we have this positive sign. Okay, what about the angular momentum of this particle with respect to point B? Now for point B, the particle's trajectory, it actually goes through point B, so R is perpendicular to 0. So this particle has no angular momentum with respect to this point B. So as you can see, angular momentum, it depends on the point you choose. So for different point with respect to different points, it's a different number. You may say, okay, why do we have this? Why are we going to use it at all? Or why do we do this definition, angular momentum of an object that's not actually going in a circle, that's going straight? Well, we're going to use it. We will use this with problems like a child running and jumping on a merry-go-round, and you will see in the next slides. So when you have, let's say, a merry-go-round, which can rotate, so let's say the kids can go on it. So we will have a child, and that child will run and then hop on it. So initially, let's say this is stationary, and because the child runs and jumps on it, it will start rotating in this direction. So this is kind of like angular collision. So to be able to solve these questions, we need this definition of angular momentum of a linearly moving particle. So in this case, the linearly moving particle is the child. Okay, here is the question that I just talked about. Now this child runs with speed v and jumps on the merry-go-round. So it could be somewhere here, 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 doesn't matter. So initially the merry-go-round is, let's say, stationary. Now we will, okay, so we will solve that problem, but here in this exercise, what we're going to do is we are just going to calculate the angular momentum of the child with respect to the center of the merry-go-round. So we will use this one. So it will be basically mv times perpendicular distance. So v is this one. So the perpendicular distance that we have to use is this one. Okay, so if you look at this triangle, that perpendicular distance is, if this is r, then this will be r times sine 45 degrees. So here you have r times 45 degrees, and it will be mv. So r is given to be 2 meters, sine 45, and 25 is m, and v is given to be 2.2. And if you do this multiplication, you will find the angular momentum of the child with respect to the middle point of the merry-go-round is 75 kilogram meter squared per second. In the following slides, what we will do is we will find the final angular speed by using the momentum conservation, final angular speed of this merry-go-round. So as I said, initially it has 0 angular speed, but because the kit is running and jumping on it, it will start rotating, in this case in counterclockwise. And in the following slides, we will find what will be the final angular speed. Okay, here's just a reminder when to use which moment of inertia. So if you have, so here's a disk, that disk is rotating around the center. So there's this string and someone is holding the string. Someone probably pushed it initially and then it's rotating around some center point. Here the disk, an object of any shape, it doesn't have to be a disk, it can be any object, any shape, is going around a center, this point. So we can use moment of inertia of a point particle. So in this problem, we would use mr squared. What about this one? Here, the disk is rotating around an axis passing through its center. So the disk is rotating around itself, not around the point, around the central point. So in this case, we have to use the moment of inertia of the disk, which is 1/2 mr squared. Here, r is the radius of the disk. Again, let's remember this table that now we are adding 2 more terms to the analogies. First of all, the net force, we learned in the previous videos that if there's net force, so this equation means net force causes the momentum change in time. So if there's net force, the momentum will change in time. If net force is 0, momentum does not change. If this is 0, then the change in momentum is 0. It doesn't mean momentum is 0. Maybe there's some momentum and it will continue with that momentum. But the change in momentum with respect to time will be 0 if F net is 0. And the same thing here. Now look at this equation. Here's the interpretation. Net torque causes the angular momentum change in time. The angular momentum, if it's changing in time, that means it's either increasing or decreasing. then there's certainly a non-zero net torque. If the net torque is zero, that means angular momentum does not change. Again, it doesn't mean angular momentum is zero. It means it doesn't change. If it's initially zero, it will be zero. Or if it's initially some number, let's say 5, then it will stay as 5 if net torque is 0. Now, also remember this equation. We can put this delta t on the other side. We can rewrite it as F times delta t equals delta p. Now, we define this as impact. That means if you, let's say there's a football or a soccer ball here, and you kick that soccer ball, okay, with your foot, so that your foot will apply some force F, and you kick it for a couple milliseconds. That will be delta t. Now, if you multiply these numbers, that will be the impact. That will give you how much momentum the soccer ball, will gain. So the impact would be equal to change in momentum. It's not a new formula. It's coming from Newton's second law. So we have an analogous equation here. Now it says if you rotate something, so if you apply a torque, rotational force, for some time, let's say I have a disk. Initially, it has 0 angular speed. Now I'm going to apply some force. So there will be some torque for some time, a couple seconds maybe. And so what will be the result of this? Well, it says it will create some angular momentum or change its angular momentum. Initially, it was 0 speed, 0 angular momentum. Now, finally, there is going to be some angular momentum. So this equation here is the rotational version of this equation. So you can think of this as the rotational impact, which changes angular momentum. Okay, let's do one example. A windmill here experiences a constant torque of 255 Newton meters. If the windmill is initially at rest, what is the angular momentum 2 seconds later? Maybe there's a wind. There's a wind coming, and that wind is creating a torque of this much. Okay, let's say for 2 seconds, and if the windmill, if it starts from 0 angular speed, what will be the angular momentum? Will be L final. So this is like you hit a ball with some force F for a duration of time delta t, and its momentum would change. Just the impact formula that I talked about just in the previous slide. So instead of this, we have now the rotational version. And remember, delta L, you can write it as L final minus L initial. Initially, it was at rest, right? Now remember, so this means I is the moment of inertia of these blades, this windmill, times angular speed initial. Well, angular speed initial is 0. So this is 0. L final, we don't know. We're going to calculate it. The torque is given 255. The time is given 2 seconds. So if you multiply these two, you will find the final angular momentum, because of the torque, will be 510 kilogram meter squared per second. Okay, let's talk about conservation of angular momentum. So if you remember when we learned about linear momentum, after that we moved to conservation of linear momentum. Now we learned about angular momentum, we will do conservation of angular momentum. But let's remind ourselves the linear case. If net force is 0, then change in linear momentum, delta P, is 0. Because if this is 0, or let's put this delta T on the other side. If this is 0, then the change, even if there's time, then the change in momentum is 0. That means, remember, this means P final minus P initial. And if the change is 0, then that means if you put one of these on the other side, that means initial momentum equals final momentum. So linear momentum is conserved and there's no net force. We can write down similar equations for the rotational angular case. If the net torque is 0, then change in angular momentum, delta L, is 0, you can see from here. If this is 0, the change delta L will be 0. That is, angular momentum L in this case will be conserved. So instead of initial momentum equals final momentum, now we're going to write initial angular momentum equals final angular momentum. And just like we expand for all particles, this term, so we basically write down momentum, initial and final values for all the particles in the system, like could be a collision, like two particles, they are coming in this way. Maybe one of them has different mass, and then they collide. Maybe this large mass after the collision goes this way, and the small mass maybe it goes this way. So they have different momenta, initial and final. So you can do it here. And the same thing, if angular collision, and you will see what is angular collision in the next slides. You can rewrite, you can expand these initial and final in terms of for each object. So basically the angular momentum of each object for initial and final cases. And finally, if you define momentum as linear momentum as m times v, we can define angular momentum as, instead of m, now we have moment of inertia. Instead of linear momentum, we have a linear speed, we have angular speed. Now, just like torque, this can be positive or negative. And how do you find what is the convention? Well, use this convention. It's positive, it's in the counterclockwise direction. Okay, so if net torque is 0, then the angular momentum is conserved. We said that, right? So then we can write initial angular for this person. Let's say this person is sitting on a stool and he's rotating around itself, but he can do one thing. He can open so he's carrying some dumbbells, some mass. So some mass here, some mass here. But he can do one thing. He can, as he rotates, he can open his arms or close his arms. Now, in both cases, the momentum should be the same, right? Because initial momentum is equal to final momentum, angular momentum. So now, because if the masses are, if they are further away from the person, like in the first case, then it will the whole object, like the person and the masses, it will have a different moment of inertia than this case. So the moment of inertia changes. So as he opens his arms, the masses go out. So the moment of inertia changes. Then but the total momentum, angular momentum, should be conserved. So I times initial, angular speed initial equals I final, omega final. So if I's change, then the angular speeds should change, right? As the person opens his arms, his moment of inertia increases. So this has more moment of inertia. This causes the angular speed to decrease since angular momentum is conserved. So to be able to only get, to balance it, if in the final case, if there's more I, then there will be less angular speed. Let's actually see the video if that's the case. So now look at this video. When he closes, he actually speeds up. When he opens his arm, he slows down. When he opens his arm, he slows down. When he closes, when he gets masses together in this close to the center, he actually speeds up. Okay, we have another example here with the marbles. They are basically rotating. All of them are rotating, and they're falling into this hole here. So again, we can talk about conservation of momentum. Why? Because there's really no force on no torque on the marbles. So the angular momentum should be conserved. Now, this person was rotating around itself. So we talked about its moment of inertia. We haven't calculated it, but it's some number which can be calculated. For the point masses that are not rotating around itself, but they're going around some center point, then we can think of these as point masses. And for point masses, we can use for angular momentum mvr. We talked about this. So here, as the marbles get closer to the center, so they're rotating and getting closer to the center, their radius decreases naturally. Since angular momentum is conserved, decreased radius causes an increase in the angular speed. So as their radius decreases, so the final radius is less, they're getting closer and closer to the center, then their speed should increase so that it balances, so that the equation doesn't break, because the angular momentum is conserved. So this whole thing should be the same. Then if the radius goes down, then the velocity speed should go up. Since marbles are going around a center, take them as point particles. So that's what we did. And let's see this video and check if that's really what happens here. So according to this equation, because the radius is going down as they get closer and closer to the center, because the radius is decreasing, their velocity when they get close to the hole, it should increase. Let's watch. And indeed, you can compare the velocity of the ones that are really, really close to the hole. They have more velocity, more speed, angular speed, than the ones, than those of the ones that are going around the circle with large radius. Okay. So now we can move to rotational collisions. We learned about angular momentum. We talked about conservation of angular momentum, just like in the linear case. And the last thing that we did in the linear case was the collisions. Now here we will do rotational collisions. Now what does it mean? What is the example of a rotational collision? Here's an example. We have a turntable. So this table is rotating this way. So the turntable is rotating with some angular speed. And a record, this is the record. Initially, it has no angular speed. A record with zero angular velocity is put on the turntable. So you put it here, and slowly you put it down. When you do it, this was rotating, and when you put the record on this turntable, they stick together. Now, not only the turntable is rotating, also the record is rotating. So they're rotating together. So they stick and move together. This is similar to the case where two objects, like two cars, one car is going this way, the other is approaching to the junction this way, and they will collide So they will become one object. They will collide and move this way. Remember, in these cases, the momentum would conserve even though the energy was not conserved. Here again, the momentum is conserved, but in this case, it's angular momentum. Now we're going to write down conservation of angular momentum. What is the initial angular momentum of both objects? Now for TT here means turntable, and rec means the record. So the angular momentum, remember the formula is L equals I times omega. So it will be the turntable moment of inertia times the speed of the turntable, which is omega 0, plus the record's moment of inertia and the record's initial angular speed, which is 0. So on the left-hand side, we have only this term. So this is gone because of the 0. Now on the second hand, the second right hand of the equation, we have the turntable and the record. They both have the same angular speed. Let's call it omega final. So the final angular momentum would be this. You can either add the moment of inertia of both and then multiply it by V final, or you can write I turntable times V final plus I record times V final. It's the same thing, doesn't matter. Now, if you want to solve for V final, this will be the answer. As you can see, V final depends on the moment of inertia of the turntable as well as the moment of inertia of the record and also the initial angular speed of the turntable. Now, is the rotation, so angular momentum is conserved, but is also the rotational kinetic energy, remember it was like 1/2 I omega squared, is rotational kinetic energy conserved? Well, it's not conserved since the collision is inelastic. Here, inelastic means, remember, for in the case of the cars, in the linear case, it will be like objects getting together, sticking together. In this case, it's the same thing. The objects are stick together, so they start moving together. And this is an inelastic angular collision because the objects merge or get stuck together. So in this case, the rotational kinetic energy is not conserved. Okay, let's make it just a little bit more complicated. Now we will add a kid that moves linearly, and we will have a merry-go-round that can rotate around itself. So here the MGR means merry-go-round, and C, the variable C, will be for child. So the problem is the child runs and jumps on the stationary merry-go-round. So this is initially stationary. That means omega MGR is 0 initially, or maybe let's put 0. So initial angular speed is 0. So what is the final angular speed of the system where the child is now here and this merry-go-round is now rotating with some angular speed? Okay, so what is the final? So what is the final speed, final angular speed of the whole, so the merry-go-round plus the child? Okay, so what we're going to do is we're going to do, again, use the conservation of angular momentum. So we will write initial angular momentum equals final angular momentum. But to be able to write this equation, of course, we need to first calculate the initial and final angular momenta. Let's start with the initial one. So the angular momentum of a linearly moving object, we'll learn about this. Remember, even if an object, like in this case, it's the child, even if an object moves linearly, we can still define angular momentum for that object with respect to any point. In this case, we're going to choose the center of the merry-go-round, because at the end of in the final case, everything will be going around that center. So the angular momentum of a linearly moving object will be the perpendicular distance times mv. So for the child, it will be m child v child times the perpendicular distance, which is just r. And notice that we are using positive sign. Why? Because with respect to this point, the child, when she runs in this direction, it's as if rotating in this direction counterclockwise around the center. So that's why counterclockwise is positive. So that's why we're using positive sign. Okay, so the initial angular momentum is just the child's angular momentum, because this merry-go-round is not rotating initially, so it doesn't have any angular momentum. What about the final case? Now, in the final case, they stick together, so it's inelastic angular collision. They're together. So now we have to find the final angular momentum. Now it's going to be the angular momentum of the child, the moment of inertia of the child times v final, because they're rotating together. So both the merry-go-round and the child, they both have the same angular speed. So angular moment of inertia of the child times angular speed of the child. This will give you the final angular momentum of the child. But this merry-go-round now, it also rotates, and it will contribute to final angular momentum, and it's the second term. Okay, now the child is not running like this linearly here. The child is not rotating around itself. It's actually going around this central point. Remember, if an object goes around the central point, its moment of inertia becomes mr squared. Of course, I have to use m child here. Now, this merry-go-round, it's like a disk. I can use disk's moment of inertia for I merry-go-round, but I am just going to leave it as imgr here. Now I can do initial momentum equals final momentum, angular momentum. It should be conserved because there's really no force. There's to create torque, and remember, if there's no torque, net torque, then the angular momentum is conserved. By the way, of course, there's some friction. Maybe this is going to slow down in time, but in this problem, we ignore friction. Okay, so initial was m child, v child times r. And the final will be this term. And it's written here. So this is the final equation that we got in this exercise. So one of these variables here can be unknown, I can be unknown, or final angular speed can be unknown, or even mr or vc. So depending on the question, you can solve for that unknown by using this equation. So we can ask again the question here, if the rotational kinetic energy is conserved. Well, it's not conserved here because even though momentum is conserved, angular momentum, rotational kinetic energy is not conserved because this is an inelastic angular collision, because they collide, basically they stick together, they become one object here. So that means that's inelastic, so that's the rotational kinetic energy is not conserved. So conservation of angular momentum, we were using this equation. And the definition of angular momentum is I times omega. This is valid for any object. This is valid for any object, because I is general here. But if we have point-like particles that are going around, it can be any shape, around some central point, then remember we can use, instead for I, here I will be just mr squared, and r is this distance. So if I is mr squared, so I can rewrite it like this. And instead of omega, I can write v divided by r. So I can rewrite this equation as m. So for initial momentum, mr initial, v initial, and final momentum, mr final, v final. But again, this equation, momentum conservation, becomes like this for point-like particles. If you have some disk, let's say like a disk like this, going around itself, around this axis, then I cannot use these equations. So I have to use this equation. And instead of I would write for the disk, I would write 1/2 mr squared. Or if it's a different object, like a sphere, then I would write the moment of inertia of the sphere. So I would look up the table and write the correct numbers and the expression. Okay, so let's solve an example here by using this equation. So the puck here this is the puck, has initial angular speed omega 0, so it's rotating with omega 0 at radius r. What would be the final angular speed if the string is pulled? So this person is pulling the string, there's a hole, the string goes through that hole, and the person is pulling the string down. What would be the final angular speed if the string is pulled down so that the radius becomes r divided by 3? So this radius, instead of r, it becomes r divided by 3. So on the puck, on this object, there's really no force, right? Well, there's a tension force towards the center. But because it's towards the center, it really doesn't create any torque. So there's really no force in these directions. So there's really no torque on this object. And again, if the torque is 0, remember, net torque would be delta L divided by delta T. If this is 0, then the change in momentum would be 0. If change in momentum is 0, then L final minus L initial is 0. That means L final equals L initial. So the momentum is conserved. Now we can use this equation. You can use either the second one or the third one. We have a point particle. Now, because the problem is talking about angular speeds, not the linear speeds, I'm not going to use the second one. So I'm going to use this one. Okay, so the initial radius is r. The final radius is r divided by 3, but don't forget to put the square here because it's part of the formula. The initial angular speed is omega 0, and final angular speed, let's call it omega final. Now, so m's cancel, r squared cancel, so what's left is 1/3 squared. So that brings a 9 on the other side. So this is the equation. Now look at the equation. If initial angular speed is 1, then 9 times 1, the final becomes 9. So if the radius goes to 1/3 of it, the angular speed increases 9 times more. So the final angular speed becomes 9 times as large as the initial angular speed. And that's actually, we saw a video, just a short clip in the previous slides. There were this hole in the middle and this some kind of round object, and the marbles were rotating, and the marbles, when they come close to the hole, so when the radius was getting smaller, their angular speed was increasing. Okay, now let's talk about work and power. in the linear case, let's remember, work done by a constant force. Remember the constant force. It will be F times D. Just a reminder, if the force was not constant like the spring force, remember the spring force, it was F equals kx. If it's not constant, then work equals F times D. It wouldn't work, so you needed to use FD graph and you will calculate the area. Okay, so that's just a reminder. Anyway, in the linear case, if the force is constant, we could use F times D. Now, what's the work done in the angular case? The work done by not constant force, but now we're going to talk about constant torque. So instead of force, I'm going to write torque. Instead of distance, I'm going to write the change in angle. And it should be, now we have to be careful in this equation. It cannot be in degrees or revolutions. For this particular formula, if you want to work in terms of joules, you have to, for the angle, you have to use radians. Now, what is that dot product? Well, that dot product here, it will give the angle between F and D. So if F and D, if they were in the same direction, then this will bring a positive. So it will bring a positive sign. If F and D, if they were in the opposite directions, it would create a negative sign, because this dot product, if you remember, it would mean F times D times cosine theta. If they're in the opposite sign, cosine 180, it will create a negative sign. Now, what is the meaning of this dot product here? Well, it means dot product gives positive if torque and rotation are in the same direction, and it will create, otherwise it will give negative, which means if torque and rotation are in the opposite directions. Let's say if this object is already rotating in the counterclockwise direction, because the angle, the change in angle, because it's rotating this way, and the torque for this force, it will be also in this way, both, so delta theta and the torque, since they're in the same direction, you will use a positive sign. But if, let's say, if this was rotating in this direction, some angular speed, that means the change in theta is in this direction, clockwise, but the torque, because of this force, will be, again, counterclockwise. Since they're in opposite directions, then you would use a negative sign here. Remember, negative work means like slowing down something, because it was rotating already in clockwise direction. Now there's some force in the opposite direction. It will not speed it up, it will only slow it down, and this is the sign of that slowing down motion. So basically, this, we would say this torque makes a negative work on the merry-go-round, so it would slow it down or even stop it. Remember, negative work means slowing down, and so it will cause the objects to slow down. Positive work would cause the increase of the kinetic energy, which means increase of the speed. Okay, if you apply a counterclockwise torque on a merry-go-round initially at rest, so this one is initially at rest, and you will apply this force, so this force will create a torque in this direction. It will start speeding up. Well, it should start speeding up because it was stationary in counterclockwise direction, so it will speed up in this direction. Now, because the torque now speeding up, if it moves in this direction, then also delta theta will be in that direction. So delta theta is basically in the same direction as the movement. So these will be in the same direction. So both of these would be plus plus, and the answer will be, so the R times F, this is the torque, times delta theta. Delta theta is like the angle that it rotates around itself. So delta theta could be, let's say, 180 degrees, but you wouldn't write 180. You would write pi for 180. If it makes one full rotation, you would write 2 pi. If it makes 5 rotations, you would write 5 times 2 pi. So here we have positive work. That means angular speed increasing. Indeed, if you apply a force like this, it will create a torque. The initial angular speed is 0, so it will cause the angular speed to increase. Now in the second case, now let's give an example for negative work. If you apply counterclockwise torque on a merry-go-round that is already rotating in clockwise direction, so this was already rotating, and you're applying a torque in the opposite direction. So the torque is opposite. So this is the delta theta and the torque, they are opposite. Torque is positive, because counterclockwise. Delta theta is negative. So if you multiply positive and negative, you end up with a negative number. That means a negative work. So this torque, due to this force, is making a negative work on the merry-go-round. So the angular speed of the merry-go-round will decrease. Remember, work is, in the linear case, it was, or in the angular case, the change in kinetic energy. It's equal to change in kinetic energy. So if the work done is negative, then the change in kinetic energy is negative. That means kinetic energy is decreasing. Okay. So this is a machine that people used back in the days to make ice creams. So it's a manual machine. So you basically apply a force and then turn this, and then it churns the milk and the other ingredients, and it makes ice cream. So you basically apply torque. If the torque required to turn the handle on an ice cream maker, so this is the torque required. How much work is done after 50 rotations? So you make 50 rotations. So one rotation is 2 pi radians. What is 50 rotations? 50 times 2 pi. So that's delta theta. And now it's in radians. Now just multiply, just like F times D. Now instead of F times D, you have to do torque times delta theta. So the torque is 5.7, and the amount of rotation in radians is 50 times 2 pi. If you multiply these numbers, you will find it's 1791 joules. So this is going to be the work done by this torque if the person rotates it for 50 times. Now, if you use revolutions like 50 here, then you will calculate something. Again, it will be energy, but it will not be in joules. It will be some other random unit. So that's why you have to use radians here, so that you can find the answer in joules. Okay, here's another example. We have a circular saw blade accelerates from rest to an angular speed of 3620 RPM. This means revolutions per minute in 6.3 revolutions. So it rotates more than 6 times, 6.3 revolutions, and it reaches the angular speed of 3620 RPM. Now find the torque. Where is that torque coming from? Well, that torque is coming from the motor, because it rotates this mill. So find the torque exerted on the saw blade by the motor. So the eye of the blade, now This blade is rotating, right? So we need its moment of inertia, 0.01 kilogram meter squared. So everything is in SI units. RPM means revolutions per minute. So revolution means 2 pi, right? So 2 pi per means divided. So this is like RPM is rev divided by min. I have to convert it to radians per second. So 1 rev is 2 pi radians divided by 1 minute is 60 seconds. Trying to convert everything to SI units. So then revolutions per minute, RPM, is equal to 2 pi divided by 60. You can do this calculation, radians per second. Okay, so the speed, angular speed that it reaches is this number in RPM. To convert it to radians per second, I have to multiply RPM because RPM is this thing. So instead of RPM, I have to write 2 pi divided by 60 times radian per second. In fact, that's what we have here. Instead of RPM, we wrote this one. So we converted the units. And delta theta, it said it rotated more than 6 times, 6.3 revolutions. Now, what is that in terms of radians? One revolution is 2 pi radians. So instead of rev, I'm going to write 2 pi rad. Here you go. Now, the work done is equal to change in kinetic energy. Remember, work done is change in kinetic energy. Of course, there's really no linear motion, so it's going to be just a rotational. So the final kinetic energy minus initial kinetic energy is written like this. Initial kinetic energy, it starts from rest. So there's really no angular speed. This is 0. So initial kinetic energy is 0. Now the final kinetic energy is 1/2. Moment of inertia is 0.01. Okay, it's given here. And the final angular speed is this number that we converted into radians per second. It's here. Of course, you have to take the square of it. Now, the work done by the motor on the saw blade is then 719 joules. It's positive. That means the work done on the saw blade increased its speed, and indeed that's the case because it started from the rest and its speed reached this number. Okay, now I'm going to use another equation that has the work done and it's equal, this is like F times D, but for the angular case, so torque times delta T. Now I know delta T, 6.3 times revolutions. I know work because I just calculated it here. So what's unknown is the torque. And if you divide this number, which we just calculated, by the number of rotations, the angle, the amount of rotations in radians, 6.3 revolutions, but I have to multiply by 2 pi to make it radians. And if you do the division, you will find the torque to be 18 Newton meters. So this torque is the torque that the motor applies on the saw blade. So here we used energy, right? Remember, in the linear case, we could use kinematics equations and or energy. So those were two alternative solutions. The same thing happens in the angular case. You can use either energy as we did here, or you can use kinematics equations like this, and also the dynamic equation like this. So it's up to you. So I'm going to leave using this alternative way to you. So if you're interested, you can try to solve. You can try to get this number 18 Newton meters by just not using the energy, but just using this kinematic equation and the dynamic equation. Finally, we can talk about power. It's work done per time. It's the same for rotational motion as well as for translational motion. It's work done per time. So here's an example. What power must be applied to accelerate an object with moment of inertia, 0.1, from rest to an angular speed of 2.5 radians per second in 6 seconds. So you have, let's say, a disk or an object. It doesn't specify what kind of object. Well, let's say it's a disk. Initially, it's at rest. And finally, it reaches the angular speed of 2.5 radians per second, 2.5. And you have to do it in 6 seconds. Okay, what should be the power? If you have, let's say, low power, you can do it, you can apply that even the small force for a long time, let's say not 6 seconds, maybe 6 hours. So at the end of, end of that 6 hours, you can get this speed, angular speed. But it wants to reach that speed in 6 seconds. Remember, the same job, if you do it more quickly, if time is less, then that means power is more. So what is the work done here? How much work is done to accelerate an object that has initially 0 angular speed to angular speed of 2.5 radians per second? First, let's find the energy. What is that energy difference? Well, the energy difference, or the work done, will be equal to energy difference, delta K. Initially, it has 0 speed, so 0 rotational kinetic energy, and the final rotational kinetic energy is given by this term. The first one is I, the second one is the final angular speed, and it's 0.3 joules. So basically, you have to provide 0.3 joules to this object to make it rotate with final angular speed 2.5 radians per second. Well, you can provide it in a long time, maybe 10 hours if you want, or 100 hours. Okay, so it's the same job. It doesn't matter if you do it quickly or in a long time for energy, but for power it matters because in the denominator there's time. So if you do this job, if you provide to the disk this much energy in a small amount of time, that means large power. If you do it, large time, longer times, that means small power. So, okay, let's calculate the power now. The work done is 0.3 joules, and it's done in 6 seconds. I don't have to convert the units because these are already SI units, joules and seconds. If you just do the division, and it will be 0.05 watts. So this will be the power to be applied to this disk to increase its speed, angular speed, from 0 to 2.5 in 6 seconds. Okay, this is the end of this lecture, so see you in the future videos.